This is 4.5 acid-base equilibria and the answers to the CA fact file for this topic. So question 1, which one of the following solutions has a pH of 1? Well, you probably know off the top of your head by this stage, having done this topic, that the negative log of 0.1 is 1. So it's going to be either A or B. But if you look at B, H2SO4, it's diprotic, so it can't be that, so it has to be A, 0.1 molar hydrochloric acid. Number 2, which one of the following salts would produce a neutral solution when dissolved in water? So you're looking for something that is derived from a strong acid and a strong base. So the ammonium we can rule out because it's not a strong base. Potassium and sodium could have come from potassium hydroxide or sodium hydroxide, so we can go with those. Potassium chloride would have come from hydrochloric acid, ethanoate from ethanoic acid, and carbonate from carbonic acid or something, I suppose, but we're looking here at B, potassium chloride, from a strong acid and a strong base. Number 3, which one of the following is the conjugate acid of the hydrogen phosphate 5 ion HPO42-? So conjugate acid has one more hydrogen ion than the thing that you're looking at. So in this case, we're looking for an H2, and the only one there with H2. So we have 3, 3, and then no hydrogen, so it has to be C. All right, now a bit of a calculation. So this is tartaric acid. And it tells you the first pKa value for the ionization of tartaric acid is 2.9. Calculate the pH of a 0.1 molar solution of tartaric acid. Assume only one H plus dissociates, which is good because there are quite a lot of them there. Okay. So if pKa is 2.9, then we can work out Ka as 10 to the power of minus 2.9, and that comes in at 1.25 by 10 to the minus 3. So that's the concentration. Well, that's Ka. And then the hydrogen ion concentration we can work out from the square root of Ka times the concentration of the acid. So we plug those in. We've got 1.259 by 10 to the minus 3, which we found in the last step, times 0.1, which is here in the information that you're given, and that gives 0.0112 mole per dm cubed. And then we plug that into pH is the negative log of the hydrogen ion concentration. So negative log of 0.112, which gives us 1.95. Quite a bit there of calculation, but it's worth 3 marks, so I suppose it's worth it in the end. Now B, if tartaric acid is titrated with sodium hydroxide, state a suitable indicator and explain why it's a suitable indicator. So stating the answer there is phenolphthalein. And then your explanation is that it changes colour in the vertical section of the titration curve. So try not to say it changes at the end point, or, that's a bit sketchy. You need to say in the vertical section of that titration curve when you plot the graph. C, then, a mixture of tartaric acid and tartrate ions act as a buffer solution using C4H6O6 to represent tartaric acid and C4H5O6- to represent the tartrate ion. Write equation to show how this buffer solution responds to the addition of acid and base. So here we have the tartaric acid adding the base to it, the OH-, and that's giving us the tartrate ion, the C4H5O6-, and water. And then we've got the tartrate ion here plus the hydrogen ion giving us tartaric acid. So number 5, explain the mode of action of a buffer of sodium ethanoate and ethanoic acid. You must use equations to explain how it reacts with H plus and OH-. So looking at the ethanoate and the ethanoic acid, we've got ethanoate here plus the hydrogen ion gives us ethanoic acid, and then the acid plus the ethanoate ion, plus the hydroxide ion gives us the ethanoate ion and water. So then your explanation is that the ethanoate ions react with and remove the hydrogen ions, and the ethanoic acid reacts with and removes the hydroxide ions. Right, number 6, and I've had to do this one very small because there's quite a lot to fit into the space. So calculate the pH of the solution produced when 0.006 grams of magnesium oxide is dissolved in 100 cubic centimetres of water at 25 degrees C. Kw is 1 by 10 to the minus 14 at 25, and it gives you the equation there. MgO plus H2O gives you Mg2 plus and 2OH minus. So what I've done to start with is, you can see it's 0.0006 grams in 100 cubic centimetres, so that means it's 0.006 in 1 litre. And the formula mass is 40. So the number of moles of magnesium oxide, 0.006 divided by 40 is 1.5 by 10 to the minus 4. Now looking at this balanced equation, 1 mole of magnesium oxide gives us 2 of the hydroxide ions. So the number of moles of hydroxide ion is the answer from the last one times 2, which is 3 by 10 to the minus 4. Then we can put this all into the equation. Kw is the concentration of the hydrogen ion times the hydroxide ion, which is 1 times 10 to the minus 14. So rearranging that, we get the hydrogen ion concentration is 1 by 10 to the minus 14 divided by, we already know the hydroxide ion, 3 by 10 to the minus 4. And we put that in, we get 3.33 by 10 to the minus 11. Finally, to find the pH, it's the negative log of that number that we just found, which is 10.48. And you'd hope in the exam paper they'd give you a bit more space than that to write it. Finally, which is the pH of a solution formed when 500 cubic centimetres of 0.4 molar hydrochloric acid is mixed with 500 cubic centimetres of 0.1 molar sodium hydroxide. So the first thing I did was to work out the number of moles of hydrochloric acid. So if it's 0.4 and 1 dm cubed, then in 500 cubic centimetres it's just 0.2 moles. That's what I've done here. 0.4 divided by 2 is 0.2. The number of moles of sodium hydroxide then again is in 500, so it's 0.1 divided by 2, which is 0.05. So our balanced equation, NaOH plus HCl, it's 0.05 and 0.2. So starting with 0.05 sodium hydroxide, that will all be used up by the hydrochloric acid, and we'll end up just with 0.15 moles of hydrochloric acid left. Put that into pHs minus log the base 10 of 0.15, and you get 0.82. And looking at the answers then, that is C. Bit long-winded for 1 mark, but there you go. Thanks.